So we finished, we were in the middle of TCP and we finished how to do checksum, and now the next thing is how to do round trip time estimation. RTT, round trip time. Why do we need to estimate round trip time? For timeout, so that we can decide when we will not get the message and we have to retransmit it. All right. So before we can decide the timeout interval, we need to do round trip time estimation, and as you can see, the round trip time has a lot of variation. So this is the blue curve here is actual round trip time of different packets, right? And so actually x-axis is not the packet but the time. So the packet that was acknowledged or sent, it's not clearly showing here, but basically had this much time and then that much time, and so there's a lot of variability. And therefore we have to be careful when we set up the timeout, because there is a lot of variability. If there's not much variability, then we can be very close to the correct round trip. And therefore we have to do mean and the standard deviation, right? Everybody knows the standard deviation, right? So because this is a random number, because the round trip time is variable, it's a random number, therefore we have to estimate the mean and we have to estimate the standard deviation, so that we can say with 95% probability the round trip time is less than this. So we want to do that kind of thing. All right. And therefore we do what we call the mean time. Mean time is called estimated RTT, and we use what we call exponentially weighted average. So a new sample comes in, a new packet, new acknowledgement comes in. So we send a packet, we write down the time, acknowledgement comes back in, we see the time. So that is our sample round trip time. Yanli, you are looking at the slides or something else? Slides, okay. All right, so sample RTT. And every time we get a new sample RTT, we update our estimate by saying estimate is equal to 1 minus alpha times estimate plus alpha times sample. If alpha was 0.5, every time we get a new estimate, we use half of that plus half of the previous estimate to get the new estimate. If alpha is 0.75, then we take more of the current new sample and 25% of the last one, and we get the new sample. Right? If alpha is 0.25, it's the opposite. So alpha could be set to any value you like, and depending upon whether alpha is small or large, the new sample counts less or more. Alpha has to be between 0 and 1, by the way. It cannot be 2. So 0 and 1. So this is called exponentially weighted average. Yeah.
Where do we get alpha from? Is it just the previous calculation?
So where do you get the alpha? No, see alpha is something that you can set in your computer. You can say I want to use 0.5. Microsoft probably has selected some value for you and you don't need to touch it. But if you were a geek and you wanted to change it, you could probably find some parameter in TCP IP thing where you can change alpha. Sample is what is in the previous graph. Sample is this blue thing. So every time a new number comes in, we plug into that formula. The red thing is the estimate. So the purpose of that exponentially weighted average is so that the estimate doesn't go as wild as the real thing goes. Okay, so it's much more stable. All right. So this is how you get the mean. We call it mean or average or estimate. Now we need to do standard deviation. Deviation of RTT is equal to 1 minus beta times deviation of RTT plus beta times sample RTT minus the estimated RTT. So we see how much is the sample away from the estimate, and we take the absolute value. We take the absolute value and then we multiply by beta. Beta is another weight. It could be, again, you could have 0.5, 0.75 and 0.25 or whatever value you want between 0 and 1, and so you get an estimated deviation from the mean. Is that clear as to what we are doing here? That we are taking the difference, taking the absolute value. So it doesn't matter whether the sample is less than the estimate, but this is estimate, right? So the thing is, less or more, we take the positive value and then multiply by beta. Then the timeout interval is estimate plus 4 times the deviation. That is fixed. The number 4 is fixed. By Van Jacobson, the guy who wrote this code. And so what we are doing is that if you had a probability density function, then you take the mean plus some multiple of the standard deviation. You are saying that this is where we will keep the timeout. The actual sample can be more than that value, but the probability is very low. That is a false timeout. That means that it is quite possible that the network can get congested and the packet made it, but you retransmitted it, right? So that is a false timeout. It was not a real timeout. Packet made it, but you retransmitted it. And the probability of that you want to keep very low. So 4 times the standard deviation. Now I got to look up in my own book, but right now, just from memory, 1 times the standard deviation gives you 67%. 2 times gives you somewhere close to 90%, and so on and so forth. Does anyone remember? 3 times will give you almost to 95 or 99.
97 and 99%.
Yeah, so this is 4 times. So really close to, basically, yeah.
But according to this calculation, this is not a really mean, this is a weighted mean?
Okay, so the question is that this is not a real mean, this is actually estimate of the mean. So it is not a weighted, this is, basically we can call it, the formula is exponentially weighted average. The formula, the name of this formula where you do 1 minus alpha times something and plus alpha times something, that is called exponential weighting, right? So this is actually the estimate of the mean, all right? Now, if you want to go to the question of what is the real mean and what is the estimate, and that's a whole new class which I teach myself, by the way. I teach a course on performance analysis. I would not go into that class right now though. Yeah.
So if you resend a packet and then you get back, after 4 standard deviations, you get back the confirmation that they received it, do you still work that into the estimated RTC?
Okay, so here's the thing, and let me just explain again one more time. Maybe your question I didn't understand. Every packet, well, not every packet. When you send a packet, you write down the time. When you get the acknowledgement for that packet, you subtract and you get the round trip time. That is the sample time. And then you use that to get the estimate. Now, for a packet which has been waiting for longer than this time, that has timed out, the alarm clock rings and says this packet has timed out, you have to retransmit it. All right? Yeah.
What happens to the first packet?
What happened to the first packet?
Yeah, is estimated just equal to sample.
Oh yeah, right. So where do you start? So starting value, you put some 2 seconds or something. So there is some starting value that you start with, and within 5 or 6 packets you will be at the closed place. Yeah.
It's the timeout interval size?
Timeout interval is what?
The graph.
Now the graph is showing timeout interval. This line is timeout interval. So this is mean plus 4 standard deviation.
Okay, so the percentage that you said
Really false would be this much. So there will be some packets. Now that maybe that is, I was going to come back to his question. Maybe that was the question he had. But basically there will be some packet which will have the round trip time more than mean plus 4 standard deviation, but they will have timed out by your method and you would have retransmitted them. Does that answer your question? Huh?
Yes.
Okay. Any other question about this? Yeah.
So alpha just constants?
Those are parameters, as we call them. Just like MSS. MSS is the most important parameter that many of you may want to change, but MSS is maximum segment size. Right? How big packet TCP should send. You could leave it where Microsoft decided it to be 576 or 5 some number. Or you could say, well, I want bigger packets. I want to send segments, my TCP to send only 1000, twice that much, 576 times 2, whatever, I mean, something like that. So you send in less number of packets. So that's your parameter, you can change it. For example, Microsoft has parameter for everything, like how many maximum window can be, how much packets can be outstanding, things like that. You can just change all of those, how many connections can be outstanding. And many people change it, and there are programs that will change it for you. So those things are not part of the protocol. In the protocol, they have given you the choice. The implementers make some choices, and the users make the other choices. Yeah.
So what happens if the packet's resubmitted? But
Yeah, they will get 2 copies. Yeah, so they will get.
what are your 2 copies?
Yeah, so the thing is, suppose packet acknowledgement is on the way, but it timed out here, and I sent a second copy. So the receiver will get it and will know that he already got it. It will send me a second acknowledgement. Remember the duplicate acknowledgement. Every time a packet is received, the receiver will say, I already got 2005 and I am expecting for 2006. And if you send it 100 again, it will say, I already got 2005, I am expecting 2006. So, and it will drop that old packet. All right? All right, so now we get into congestion control. Yeah, question.
Wasn't it we went over slide 36, which is connection establishment and teardown?
Oh, yeah. All right, we go back to slide 36, which we skipped by mistake. So the connection establishment is it's what we call a three-way handshake. Three-way handshake means when somebody wants to connect to somebody else, let's call it A and B. A sends a message which says SYN flag is set. If you remember, what was the SYN flag for? Was synchronize. And it says ISN. Initial sequence number is 100. So my first byte, whatever I send you, will have number 100. And we said that that number doesn't have to be 0. Right? We went through the discussion as to the first byte doesn't have to be number 0. So my first byte will have a number 100, and this is the first packet. So this is basically when the SYN flag is set, that means this is a new connection. By the way, we generally in our daily talk we call it SYN packet. This is a SYN packet because it has a SYN flag set. Then when this one accepts it, B accepts it, it sends a packet which says SYN, synchronize. I want to start a connection 2 with you, and that means I accept your request. My initial sequence number is going to be 350. I am going to start counting from 350. My first byte will be 350, and ACK 101 means I got everything up to 100 and I am expecting 101. Hopefully there was a byte 100 there. It could have been that there was 100 byte, then we'll say 201. All right. So this one says this is a new sequence number. SYN means there is a new sequence number space. Initial sequence number is 350 and I am ACKing 101 means that I got up to 100 and I am expecting 101. If there was no data here, then it will say ACK 100 means I got everything up to 99 and I am expecting 100. Yeah.
Where is the initial sequence number set? Where is it stored in the TCP packet?
Okay, so sequence number space is there.
Also, just the sequence number?
Yeah. Alright, so this is stored in the sequence number space. Now, this one is ACK. 351. So now this one will say, I got everything up to 350 and I am expecting 351. Once those three messages are exchanged, then the connection is set up. Right? Before this, it is called half open connection. Means I want to talk to you, but I haven't heard back from you. So this one sends a message, and then it keeps remembering that I sent a message to already to B. I want to really get that web page from them, but I first set up a connection, and then I haven't heard from them. And so this is a security attack. Why this is a security attack? Is because somebody can send you 2 million SYN packets. So they send you 200 million SYN packets, and you told them, look, okay, I accept your connection, but they haven't sent you the last stack. Right? So you have 2 million half open connections. All your memory is exhausted, and the real people cannot get in. So this was one of the older SYN attacks. Now Microsoft makes sure that you cannot have more than 50 open connections. Actually, no more than 10 open connections. So you cannot create more than 10 open connections. So if you are doing BitTorrent, how many files are you downloading? Sometimes. And for each file you are making how many connections? Right? So that 10 number that Microsoft has set for you is not good for you. Right? So one of the things that the torrent guys will tell you is that change that number. Number of half open connection. Right? Yeah, go ahead.
But the number of half open connections isn't a real limitation because it's only
Yeah, right. But you cannot do it faster. That's good point. The point is the number of connections is not limited. You could still open 2 million connections. You could still download 2 million points, but you cannot. So yes, number of half open connection cannot be more than 10. Number of open connections can be any number. Right? But you will find out, you just do this. You change the number of half open connection, the download rate goes up. Okay? And there are programs on the net that will do it for you. And they generally change it from 10 to 50. That's all they do. But you understand the need for changing that, right? And so this is a three-way handshake. And three-way handshake means that the third message has to come in, otherwise the connection is not set up. All right, how do you disconnect? You disconnect with the fin flag. Fin means finished. And so this side wants to close the connection. It says, I am finished. This guy says, okay, I got your message up to byte number 300, whatever number, we got it, and I'm expecting 301, whatnot. Then this may not want to close it, because it has still some data to send. Right? Then it will send more data, and then it will send a fin. When this guy wants to, this side wants to close it, then it sends a fin, and then this side sends an ACK. All right? When this ACK is received, then you are done. Right? If this ACK is not received, then you are not done. I mean, obviously what is happening is, after this fin, probably it went away to sleep anyway, but you have some data to send, you sent it. If this data is not acknowledged, you probably are going to retransmit that data. All right? And for the timeout also there is a limit. I mean, you don't retransmit after more than 4 times. You transmit 1 time, 3 times, 3 or 4 times, and if there is no acknowledgement, you close the connection and go home. All right? So you need this final acknowledgement just to be sure that everything is gone. Yeah.
You can only close though after that final acknowledgement, and you're not getting.
Yeah, if you don't get it on 4 times, then you're done.
You're not getting an acknowledgement to close then. You just close it anyway.
Yeah, they will close it. See, that's the thing is that closing is by timeout then.
Okay.
Yeah.
So what happens if one side initiates a fin, the other side still have lots of data?
Yeah, they will continue. So it's quite possible that this side is a simple request. It finished that request, and now it is going to send, and one next day it will close it. So fin simply means I'm not going to send you any more data, but I'm going to receive it.
So there is an understanding that the initiating side will respect and wait for the other to finish.
Okay, so there is no initiating side. Okay, so the question is, if A opened the connection to B, who can close it? It doesn't matter who opened the connection. Anybody can close it. So B can close the connection first and say, well, I'm done. All right? And then A could be doing the fin later.
Regardless of who started the connection,
Yeah.
suppose that I want to finish the connection,
Yeah.
but the other side doesn't want to.
Yeah. Then you just have to.
Acceptable that
So that would be another half open connection in some sense, because you closed it, but the other guy doesn't close it, so they can hold on to this act, but that will have a timeout and will go away. See, this one doesn't have a timeout. This one actually, let's see what will happen. Here you send a SYN and then you don't get the acknowledgement, so just that the number of connections would be, half open connections could be too large and that could exhaust your resources. Here I think similar thing could happen though. I mean, somebody could send a SYN fin and then they could do the fin attack. But I haven't heard of fin attack. I have heard of SYN attack. SYN attack is a very famous attack. Okay, so we have a three-way handshake, and you can close with a fin flag set, or you can close with abort. So there is a abort command too, actually abort flag, and that could just, that simply said forget it. That's really not a neat close, right? You just you don't know whether what made to the other side and whether they made it or not and all that. So abort is also a possibility. Yeah.
What if your computer just dies and
Yeah, that's one abort. I mean, basically that will time out. So yeah, right. So that's what happens many times. Then the computer has transmitted 4 copies of something and it didn't make it, then it gives you an error message saying that site is not reachable, or something like that, connection broken. And yeah. Oh, abort is control C. I mean, so thing is generally when you write a program, when you run a program, you want to go to the exit, quit, and neatly close it. If you control C in the middle of something, whatever was happening is, basically you are leaving in the middle.
Like brutally close it?
Yeah, forced close. And that's simply a flag there somewhere, abort flag. Let's see, urgent reset flag. Actually, reset is much more gentler than abort, so I don't know. I mean, maybe reset the connection. Yeah, reset is the only thing. So reset is probably used for abort, and that means that you have to resynchronize. You will have to start. If you want to send any more data after this thing, then you have to start with SYN again. Otherwise, you close. Yeah.
How was the data being sent when you aborted?
I'm sorry.
How was the data being sent when you abort?
Yeah, it will just come and be dropped.
Like dropped in like the SSH?
Yeah, it could be. Basically, that's what will happen because routers don't know anything. So basically, all the packets that are traveling will make it there when the connection is not there. And what will happen is the TCP will see that there is a packet for a port number and which it is not open anymore.
How to know that packet coming to that port number isn't trying to initiate a connection?
And so basically, yeah. So for example, if I had a connection with this IP address and that IP address, and then so when it comes, I know which user to give it to, right? But when something comes from that IP address and I have no user, Just drop it, and that comes all the time. There are lots of packets which are just being dropped. Alright, so we now know how to open the connection, close the connection, we know how to do round trip time estimation. Now we go into congestion control. So congestion control is different than flow control. Flow control is between the source and the destination. The congestion control is making sure that there are enough buffers in the network. If there are not enough buffers in the network will drop our packet. Will drop our packet, and 1, 2, 3 people are sleeping right in the class. I don't know what to do. What was the solution?
I had a teacher once that threw paper airplanes at students.
Paper airplanes, okay. Well, I kind of have sympathy with people because they are working very hard, they are working all night, and then they come to the class. So, I mean, I know how hard you guys work. So, I don't know what to say, but at the same time, maybe you need to take coffee, or you need to just not come to the class, or do whatever it is, so that at the same time, coming here is worth the time. Anyway, so now that everybody is awake, by the way, so that's fine. And so window flow control. So window flow control basically, windows are used for flow control, but what do we do for congestion control? So again, now this is my beginning of my networking career in 1978, and this is a new discovery. The new discovery is that when you lose a packet, that means the network is congested. It sounds so trivial today, but a paper was published in IEEE Transactions on Networking, authored by me, saying that. Okay. Now, why it was a new discovery? Because in those days we thought when you lose a packet, you just retransmit it. That's it, period. Nothing else. And what this paper said, that you don't retransmit it. If you lose a packet, wait and reduce your window. If your window is 8, make it maybe less, so that you reduce the load on the network. So that was the new discovery. And now it is a standard method, by the way. Now it is in TCP and everywhere else. Okay, anyway, so now it is a standard method. So what it is that the timeout is a good indication of congestion. And when you get a timeout, you do not simply retransmit, you change the window down. And my work said that you change the window to 1. You change the window to 1, and then you go up slowly. So there is a lot of history behind this, and if you go to my website, you will find lots of papers on congestion control which we published in those days, and we went to IETF and we presented to IETF, and IETF adopted some of it. And then we did some additional work where we had explicit bits coming in, and then we said you should go to half, and then you do this and that. So there was a lot of this thing. So some combination of this was noted by Van Jacobson, who was the guy who was writing all the TCP code, and he adopted some of it. And that is called slow start. So the slow start is what you use today on the internet, and it is done for you. So basically you don't have a choice much, basically implemented by Microsoft and everybody else. So this is how it works, that when you start a new connection, the window is 1. And then you go up slowly, go up, and then you go up to the receiver's window. Receiver says you can send me 8 packets, you reached 8 packets, now you cannot go anymore. Then if there is a timeout, you go down to 1. And then you go halfway slowly. So receiver says go to 8, you go up to 4, slowly up. And then you go even more slowly. And if you have a timeout, you go back to 1. And now you go half of this new value, and so on and so forth. So this is called a slow start. A slow start means you start very low first of all. So you don't, even though the user says, so for example, receiver could say, well, I have 2000 buffers, please send me 2000 packets. You're not going to send 2000 packets. You're going to start from 1. because we don't know whether the network has 2000 buffers or not. We start from 1 and keep going, and you go it exponentially up. As you can see, this graph is exponentially up. All right? And then you come down, and then you go exponentially up halfway, and then you go linearly up for the rest of the way. So there was a lot of discussion in those days as to whether linear should be up or down, should be this and that, and whether you should go down to 1 or not. So there are lots of papers in that area. But this is a slow start, and you should know this by heart, because this is the heart of the TCP now. And there are 900 to 1,000 papers every year, even today, published on fixing a slow start. If you want to do a research in networking, if you don't have a better topic, just go and fix a slow start. It's not going to make any difference, because nobody has the same power that Van Jacobson had in those days. He was sending out the code for the Unix TCP. Everybody was using Unix. Everybody was using the Berkeley distribution. So he could implement anything, and then everybody has to use it. But today we don't have that power. So anyway, but this is a very favorite topic for everybody to do research. I don't do any research anymore in this area, but I'm just telling you that this is this is the heart of TCP research. All right, so let's see. Let's go see if we have missed anything. Now the exponential growth phase is, yeah.
Could you go back to the graph, please?
Yeah.
What's the idle interval?
Yeah. So suppose you reach up to this point and there are no more packets to send. Then you keep your, so there are two windows here, the receiver window and the source window. The source will keep its window right here. And then it may time out, or something like that. So during the idle interval, you don't change the window. Basically, the idea is you go up exponentially or go up linearly, but if you have nothing to send, then you don't go up.
Okay, so why does it go again? Why does it drop down again?
Oh, if you have, okay, see a thing. So there is an interval for which the state is good. Suppose you didn't send anything for 1 day. Where are you going to start from? Where you left off yesterday, or are you going to start from 1? Because after 1 day, the state that you measured yesterday is no good. Right? So you start from 1. So there is some seconds or minutes interval after which you start from 1.
And does it ever stops and never, like if there aren't any timeouts, does it?
Yeah, like this. So if the receiver set some value, you reach that value, then you stay right there forever.
It's blocked by the receiver.
Yeah, now it is blocked by the receiver. So I want to go back to the previous slide though. The previous slide says it is blocked by this. So this is called CWND, congestion window. The thing that I had plotted, which I call the source window, that is called congestion window, CWND, and it is measured in units of the segment, not in bytes. Okay, the window is measured in bytes. If you remember in TCP, we acknowledge when we say 100, we mean 100th byte. But when we do here, we mean packets, segments. And so what you do is you take the bytes and divide by MSS, which is the maximum segment size, 576, divide by that, or 512, whatever number, and that gives you some number of segments. So that's what we are using here. This is a little bit complicated. I just want to make sure that you understand the difference. So CWND of one segment, and so you just go up by 1 and increase window by 1 MSS every time an ACK is received. So every time you get, so you send one segment and you got the acknowledgement, you go to 2 segment, you got 2 acknowledgement, you send 4 segments, you got 4 acknowledgement, you send, like that.
So it's not the add ones.
Okay, well you got 4 acknowledgements, you add 1 for each of those. Every time you get an acknowledgement for one segment,
So you add like
so basically in one round trip, suppose you send 100 packets, you will get 100 acknowledgement.
so you add 100 or you add
So you add 100 because so the thing is, okay, so it doesn't matter. You are not counting the number of acknowledgement. You are counting the number of packets acknowledged. So it could be just one acknowledgement, but it says I got 100 packets. So that is 100. You go up by 100. So whatever number of packets are acknowledged, you go up by 1 for each of them.
So why is it exponential?
Oh yeah. Okay. So let me do it again one more time. Why is it exponential? So first you start with 1. How many packets will you send? 1. 1 acknowledgement will come back. So your window will become 2. You will right away send 2 packets.
Okay.
In the next one round trip, in one round trip, how many acknowledgements will you get? Now again, it could be one acknowledgement. How many packets will be acknowledged? 2 packets will be acknowledged. So you will send 4.
Because the speed goes up, then you get more acknowledgements.
So this is why it is called exponential. Yeah.
So if you're like have a TCP connection with the HTTP server, and you're requesting just like a small web page, isn't that like severely slowing down
Yeah.
web pages?
Yeah, so mostly your web pages are coming at this window. And so this is not good for short transfer. And so that's the price you pay. Yeah.
So you increment by 1, then give a timeout, you increment by,
Okay, so when you get a timeout, you go down to 1 again.
right?
And then you go exponentially up to halfway.
The same intervals though?
What do you mean the same interval? Basically, round trip is whatever it is. I mean, yeah.
1 for,
For every acknowledgement, you go up by 1. Now, here is the name thing is to remember. This part, which is exponential increase, which in my view is fast increase. Now, Van Jacobson named it slow start. And this part, which is linear increase, which in my view is slow increase, he named it, what did he call it? Name will come up. Okay, this is called congestion avoidance phase. Congestion avoidance phase, so that name is appropriate actually, because we are trying to avoid the congestion. And this slow start actually is, and his point of view is that we are really starting low, and therefore this is slow start, right? So that's fine. So basically, when somebody says slow start, you should know right away what we mean, because this is one of the most favorite topic and for networking research. And then so basically you go from 1 exponentially up wherever you need to go up to, and if you fall down, then you go halfway. So you have to remember where you fell off from, and half of that is called SS threshold. SS threshold means slow start threshold.
You start from there?
No, you don't start from there. You go exponentially up to that point, and then you go linearly. What is linear? In the linear phase, you go window up by 1 for every window. So if your window is 100, you get 100 acknowledgement, you go up by 1. So that means 1 round trip, you go up by 1. Second round trip, you go up by 1. Third round trip, you go up by 1. So that's why it is linear in time. Okay? Alright, so when you start, you remember the SS thrust equal to CWND by 2. So this was your CWND, congestion window. And you drop down, so you remember you set the SS thrust to half. And then you set the CWND to 1. And then you increment by 1 until the SS thrust. And you increment by 1 upon CWND afterwards. 1 upon CWND means basically 1 round trip you go 1. So these 4 lines should be clear to everybody. These are what is written here, these 4 lines. If something is not clear, please ask right now. Yeah. Go ahead, you go ahead.
So SS thresh, when the receiver window and when you get a timeout aren't the same, do you go to half?
No, okay, in this example they are the same right here, but here they are not same.
So if you get a timeout and you were not at the receiver window, do you go?
Yeah, it doesn't matter where you are. So suppose you have a timeout here. You put it half of that as SS thresh. It's not very clearly shown by scale, but if this was, let's say, 7, you will set it at 3 or something like that here.
So it's half of wherever you had the timeout?
Yeah.
Not of the receiver window?
Nothing to do with the receiver window, no. Yeah.
How do you decide if to go exponentially or to go linearly?
Oh, you just decide by SS thresh. If you are below SS thresh, you go exponentially. So in the beginning, SS thresh is right here at the receiver window. In the beginning, SS thresh is at receiver window, so you go exponentially all the way up.
Okay, so the beginning is set like that.
Yeah, and now suppose you didn't reach there and you dropped right from here, then you will set the SS threshold to half of that. Yeah.
In the third line,
Yeah.
the increment per one, that's the exponential function?
That's the exponential function, yeah.
Then isn't it supposed to be like increase times 2?
See,
Max you
you have to remember this one. Increase per act, 1 per act. I explained this before. In one round trip, how many acts will you get? Equal to windows.
get the number of the
Yeah, so this is 1 per act, 1 per packet act.
Yeah, but it's not. You said you multiply you get like 2 acts, you send 4.
When you send 4, how many acts will you get back in the next round trip?
4.
4, right. So your window will go up by
By 2.
4.
No. Okay, the next round, yeah, by 4, yeah. So it's not.
It will go 1, 2, 4, 8, 16, every round trip like that. It will go exponentially. Actually, this is the homework, by the way. So you will have to do this. Remember, you have to be clear about this. Yeah. Question? Was there a question here? Not clear? If it's not clear, ask again. I can do it. I said that the window, even though it goes up by 1 every act, but if you were to plot as a function of time, it will double every round trip.
It might be useful to put an example on the board.
It might be useful for an example on the board. So this example is it might be useful to have a homework. And so this is the homework, right? And basically you can see that how the window is going up, and then there's a linear phase, and then it goes down to half. So it goes down from 43 to 21 or something like that. No, actually this is too early to talk about that. So let me just go back to where I was, and then we will show you the modifications. But basically, I think key thing to understand is that it is linear with the number of packets, but it is exponential with time, because the number of packets per round trip is doubling. Is it clear to you or not? Not clear to you? Shall I?
I understood what happens, I just didn't understand the phrase.
Oh, now you understand?
Yeah.
Okay, is there anybody else who doesn't understand? Somebody said I can do example. So example is very easy. I mean, basically, you start with 1 packet and you get 1 acknowledgement, right? Now you send 2 packets back to back. Now you get 2 acknowledgements. Now, so your window was 1 here, it became 2 here, it became 3 here. How much will it become after this? 4. So how many packets will you send? 4. In fact, you might even send right here. But anyway, so let's say you send 4 packets. Right? And then you get the 4 acknowledgement back. What will be your window? Here the window will be 8. Right? Now how many round trips you had? I mean, if you just ignore the distances between the packets, you have 1 round trip, 2nd round trip, 3rd round trip. Right? So that's what I'm saying. Every round trip the window doubles. Yeah. So right now, then in the linear phase, when you got this acknowledgement, you increase only by 1/3. When you got this one, you increase by 1/4.
So shouldn't it be 1 divided by C window?
The window, yeah.
MSS?
Yeah. 1 MSS by CWND. So basically, MSS, forget MSS. 1 by CWND. Okay? Alright. So, after a long ideal interval exceeding 1 round trip, set the congestion window to 1. Exponential phase is also known as slow start, and the linear phase is known as congestion avoidance phase. Now there is another, yeah, sorry.
Real quick, if they receive a packet and before they send the acknowledgement, they receive another packet, they just send one acknowledgement that
Or is it
Yeah, so the thing is, it doesn't matter how many acknowledgements you receive, these two could be one acknowledgement.
Okay.
You just have to count how many packets were acknowledged.
You need to remember how many bytes you sent in each packet.
Yeah, right. So how many bytes were acknowledged, and you divide that by your MSS size.
None of the packets are MSS size. They can be smaller, right?
Yeah, right. So you divide by MS. Your packet could be 256 byte, or MS is 512 byte. That is only half a packet, half a segment. That's right. And this is complication. I know this is complicated, but they decided to do this slow start in integers of in the multiples of maximum segment size,
Okay, so it's always.
not in bytes. Okay. All right. Now there is another principle, AIMD, and lucky us, we were at the beginning of this revolution of congestion control, so we invented this AIMD, and I'm teaching it here because the book talks about it, and not because I want to teach you my research, but the book talks about it. And so this is our paper in 1989, which has, again, I think about 2,000 references, citations, something. So one of the highly cited papers. But the principle is very simple, is that if there are two people and they don't know each other, how would they increase or decrease? So we came up with the principle called additive increase and multiplicative decrease. Means whenever you want to go up, you should go add some number to your window. When you want to go down, you multiply some number to your window. Additive increase, multiplicative decrease. If everybody did that, then everybody will reach the fair point. And we can show that very easily with two people. So here is one person W1 and here is another person W2. And the total sum, suppose the network can take only 8 packets. So W1 plus W2 equal to 8 is this line. If you send this many packets, then the network is efficient. Network is fully utilized. If you send any less than that, then network is underutilized. If you send any more than that, then network is congested. So this is called the efficient line. This one is W1 plus W2 equal to the network buffering capacity. On the other hand, this line is fair line. If you are on this line, then W1 is equal to W2, means both of you have the same window. And really our goal is to reach to this point, which is fair and efficient. So both of us have the same value. So how we reach that point? We could start from any point, and if we do additive increase and multiplicative decrease. Additive increase means we draw a line which is 45 degree. We both go up by same amount. Suppose we all decided we will go up by 2. Then I go up by 2 and you go up by 2, that we go along a 45 degree line. When we want to decrease, we do multiplication, so that we just basically we go to a line which goes to the origin. We both go down by half, let's say, right? And we increase again, we decrease again, we increase again, and you can continue this and you will end up at this point or close to that point, depending upon what your multiplication factor is or not. So regardless of where you are, and the same thing applies to n people, AIMD principle takes you to a fair and efficient point.
How do you know you're over your capacity?
Oh, because you will lose. Packets will be dropped. And how do you know you are below? Because packets will not be dropped.
So you always try to go up until packets drop and then.
You go down multiplicatively. Yeah.
Is this the fairness question that everybody talks about?
No. So there is another one which is called fairness. Among this, we had another called Jain Fairness Index. So fairness index is not talked in the book, I think. So I am not going to talk about it. But basically, so this one related to this was that if you are not at this point, then what is your fairness as opposed to that point? There it is fully fair, 100%. One fairness is 1. Here there is some number, and so we had a formula for that too. I am not going to go to that, but basically, so the idea is AIMD principle, which has stayed now so far. Everybody now takes it for granted, and obviously we get a lot of credit and all that for this. But basically, so the idea is simple: is that you always go up additively, come down multiplicatively. And if everybody did this, so regardless of how many people there are, you get you get fair efficient point. Yeah, question.
How do you decide by what number you
Yeah, that's your parameter. This is just like other alpha parameters we saw, that you could decide to go up by 1/8 or one window, or you could decide to go down by 1/7/8. So regardless of what parameter you select for multiplication or for addition, this is always fair and efficient.
Not very interested how this connects to what you just talked about.
Oh yeah, because the thing is, this thing came about from that AIMD principle.
Okay, so the
So,
top one is the.
Yeah, so the going down to 1 is multiplication by 0. So that also we invented. Basically, we said, okay, so now we have to go down to 1 and go down to some value, go down by multiplicatively. So we said, okay, why not half? We tried half, it didn't work out. We tried 1/4, didn't work out. So finally we said you have to multiply by 0, basically you have to come down to minimum. So you go down to 1 means multiplication, and then you go up additively.
You have two kinds of slopes going up. You have the.
Yeah, right. So that is Van Jacobson's design. See, in our own design, we published a similar paper. We had only one way to go up, but Van Jacobson selected 2 ways. I mean, see what happens is when the research is being done, different people are saying different things, and maybe there was somebody who was saying we should go linearly, and we were saying go exponentially, and I forget which one we were on. But so Van Jacobson said, okay, halfway I will do this, other halfway I will do that.
So the AIMD is like a theory, and this.
Yeah, this is AIMD, and the book talked about AIMD, and I don't know why, but so I said, okay, I mean, if they are talking about, let me just explain it. So anyway, so the idea is, all of that research took a slow start, and then people started fixing slow start. So as I was saying, this is a very topic, very strong topic. So as soon as a slow start was implemented, then somebody came up with fast recovery. And by the way, TCP versions are not numbered like version 1, version 2, version 3, version 4, like any other program. They are versioned by the cities in Nevada. Okay, so this is the Tahoe version, this is the Vegas version, and this is the Reno version. All right, and only those guys who work on this can remember which is first and which is later. All right, so I can't remember it, but anyway, the TCP Reno, which was after Tahoe, and I don't know why Nevada, in the first place. We have so many states in the country. But so TCP Reno implements another modification to a slow start, which is called fast recovery. All right, and the fast recovery says that if you get a duplicate acknowledgement, that means some packet has been lost. So you don't have to wait for a timeout. If you get a duplicate acknowledgement, suppose you send something and you got, somebody says, I got 100 and I'm waiting for 101. You send something more and then they say, I got 100, I didn't get 101, means they didn't get something in between. Right? So when you get a duplicate acknowledgement, that is already an indication, so you don't have to wait for timeout, you could do something. And it doesn't have to be as bad as timeout, you could do something less aggressive. So that less aggressive thing is called fast recovery. So that less aggressive thing says that what we will do is when you get 3 duplicate acknowledgement, not 1, you get 3 duplicate acknowledgement, then you retransmit the missing segment, set the threshold to half, but you set the window to that threshold plus 3. So you don't go to 1, you just go to half plus 3. And then you will go up by 1 every duplicate ACK. Every subsequent duplicate ACK, well, every subsequent should be ACK, I think, it should not be duplicate ACK. For every duplicate ACK, basically you enter the linear phase. So this is how it works. I mean, let me see. I wish I had a graph here, but basically what happens is, actually the graph was there in the homework. Let me just show you this one. This one here, you got a 3 duplicate acknowledgement, so you didn't go down to 1, you went down to half, right? And then you entered the linear phase.
But why is linear? It's one. You increase by 1 for each act.
This is 1 upon CWND, yeah. So that basically should be, so that is where for every duplicate act CWND equal to plus 1, I have to check that out as to why first of all, I'm not sure why it says duplicate here, and then it says so, but anyway, but basically the summary is that in fast recovery, you don't go down to 1, you go down to half, and then you go linear phase. All right, and if you want a real flow chart, then here is the diagram. This is, by the way, called state diagram. State diagram means TCP could be in one of these 3 states. It could be in the slow start phase, it could be in the congestion avoidance phase, it could be in the fast recovery phase. So this is a new thing which was invented by the people who invented fast recovery, that you need 3 states before. Oh, it's my computer. All right. So before this, there were two states, only slow start and congestion avoidance, and we kept circulating between those two. But now there is a fast recovery. So basically, let's read line by line very carefully. When you are a slow start, there are many things possible. So the way, have you seen this kind of state diagram before? Most of you? Okay. So these lines indicate the events, and one side of the line is the action, and other side might be a condition. So for example, when you are in the slow start phase, if you get a duplicate act, all you do is duplicate act count plus plus. Yeah, right. If the duplicate count act becomes greater than 3, right here, this equal to 3, then you go to this event and you go there. But plus plus everybody understands, right? Okay. Here that is a different state, and then we will worry about that. But as soon as this count becomes 3, you go there, right? There is another thing, that if you, as soon as you send a new segment, new act, you get a new act, you set the window to window plus 1, and you set the duplicate count to 0, and you transmit the new segment. When the window goes over SS thresh, you enter this state. If in this state you get a timeout, you go there and you do this. In this state, if you get a timeout, you stay in the same state. In this state, again, if you the duplicate, if you are here and you get duplicate act. Oh, here I think that's what the last sentence was about. Is that as long as you are in this state, every duplicate act will increase your window. And once you get out of this state, then you will get into congestion avoidance phase, where you will get a fresh act. Once you get a fresh act, this is the line, fresh act. Let's see, this line is, where is the condition for this line? This is timeout, and this condition is missing here. But basically, when there is a fresh act, you come here, and you are in this state, and this is the linear increase. All right. And if in the linear increase you get duplicate act count again, then you come down here again. Yeah. Go ahead. Question about this? Yeah.
So to get a duplicate act, you have to first time out, right?
No. Okay. The question is to get duplicate act. Anytime the same old packet is acknowledged again, that is a duplicate act. That is much before timeout.
So why would they send it back again?
Or why would they send duplicate act? Then because they receive something out of order.
Why do you set it to SS threshold plus 3? Receiving no,
Yeah. And don't ask me that, because see, thing is, somebody who did the research, they did the analysis and they figured out plus 1, plus 2, plus 3, plus 4, plus 5, and plus 3 was the best. So this is some simulation result. Okay.
What's the importance of the threshold in the case that you start above it?
Yeah, right. So basically, so summary is this, that they said that you don't have to go down to 1. With the duplicate acts, all you have to do is should go down to half. And again, there is a whole simulation which must have said that the 3/4 is not good enough, 1/4 is not good enough, half is the best. So anyway, so the thing is, on if 3 duplicate x, you go down to half.
Okay. So the weird thing is like you start above it, you start at
Plus 3.
right.
Yeah.
So what does it mean?
Or because you have 3x. The thing is, for every duplicate x, they want you to go up by 1, so you already have 3.
Just thinking, you start above the threshold. So what is the importance of the threshold? You could have put it to 1.
Yeah, no. Basically, first of all they're saying is that skip the exponential phase.
Yeah.
And you are already in the linear phase, you already got 3 acknowledgements, so go up by 3, and if you get more duplicate acknowledgement, you go up more, which doesn't make sense to me. Okay, because more duplicate acknowledgement means the network is congested, some things are getting lost. I wouldn't go up, increase my window more, right? But that is my point of view. This is what is implemented.
But the threshold is never used.
Or threshold is never used, but it may be used if there is a timeout. So the thing is, the threshold is used to decide. There is a code written up which says that if you are above the threshold, go linearly. So that's where the threshold is used, just to make sure that you go linearly. All right. So this diagram is the most detailed diagram. As I saw that there is something still missing in this, which is this line is not correctly labeled. But other than that, all our lines are labeled. I noticed that this has 2 lines. This is labeled timeout. This is labeled duplicate act. This has 2 lines, which is one is duplicate account. This is not labeled. But anyway, so this is the state diagram.
If you're at fast recovery and then you have timeout, you divide the threshold by 2.
Okay, so right here, if you're in the fast recovery, if you have a timeout, this is what you do. You basically, wherever you are, you're right, you're going almost the right direction. Wherever you are, you take half of that and make the threshold. You make that threshold and you go to slow start. All right, that's all about congestion control. So then some people measure the relationship between probability of loss and the throughput. And in fact, it's not a measurement. They also analytically proved that if you do whatever you are doing here in slow start kind of stuff, then your throughput will be equal to 1.22 times MS divided by RTT square root of P, where P is the probability of loss. Now, it would be nice if we had a simple explanation of this that we don't have right now. So we'll just use this formula and know that there's a formula exists, which is the average throughput, and the book talks about this formula. So I put it here. But that's the end of that one. Okay. Anyway, that brings us to the end of this whole chapter actually. So this is the 5 points that we learned. First is that the UDP provides flow multiplexing and optional checksums. This you know by the homework, by the exam now. Both UDP and TCP use port numbers for multiplexing, the same port numbers. TCP provides reliable full duplex connection, and TCP is stream based and has credit flow control. So basically credit is another word for window, and we use it in byte based, right? And then slow start provides congestion control, and we saw all this details of slow start.
Credit flow control?
Okay, what is credit flow control? Credit is another name for window. Yeah. The reason it is called credit is because the receiver gives you a credit, says that okay, you can send me 2,000 packets. So you say, well, I have a credit line of 2,000. I can draw as much, I can write checks as many as I want, up to $2,000. Right? Once you run out of credit, you cannot send anymore, spend anymore. All right. So this is the homework now. Let's see the homework. It says, assuming TCP Reno is the protocol experiencing the behavior shown above, answer the following question. Above means below actually here. Answer the following question. In all cases, you should provide a short discussion justifying your answer. So, answer the question. So, all of these questions, when it is a slow start, when it is congestion avoidance, blah, 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 all of these. Okay? And once you have done this, you will understand everything about slow start. Up to K. All right, this is due Monday. Then we have the whole summary of the whole chapter. First, that was summary of TCP and UDP. Then before that, we had a few other points. So let's just go by those 3 points. Multiplexing is done by combination of source addresses, source and destination IP addresses and port numbers. Then we learned about alpha. Larger alpha means larger window is better. And then we remember that principle where, if you want to change one thing, you have to change the other thing so that the alpha remains the same. And therefore, window flow control is better for long distance or high speed network because they have a large alpha. And then we talk about UDP and TCP.